Yeah, so in this last video for today, I want to go over the PyTorch API in particular, discussing the subtle difference between the object-oriented and functional APIs, because it will become useful in the future lessons. So here is an overview of a multi-layer perceptron. So we haven't really talked about in detail how it works. I only showed you some graphs of how it looks like. So here for this purpose, it's really just sufficient to think of it as a multi-layer neural network, because the same concept really applies for all types of networks when we work with PyTorch, or almost all types of networks. So there's like this general template that you can think of, where we have, or where we use usually a class to define the model, and then for this class we inherit from this torch.nn.module. So this gives us some certain convenience functions automatically. So this is usually how we set up a network in PyTorch. And then there's this constructor, the init constructor. That is something we can define ourselves. So there's one line that we use here. This is really just for inheritance, so it inherits the init method from a module, but then everything else here is something we can define ourselves. So here I'm setting up a neural network with two hidden layers and one output layer, and each layer is a torch nn.linear, a fully connected layer here. And these are really in the init method only the parts that need to be updated, like the model parameters. So how the network runs, like the forward pass, that is what we define in a forward method. So here, the input to the forward method is just a data input that will be provided during training. And then we define really how the computation works. In this case, this is a network where we first compute the net input, then we use the ReLU function. We discussed a ReLU function earlier in this lecture. Then we have another fully connected layer, net input, then another ReLU, and then the output, and then we compute also probabilities for the output. We could technically skip this step and only return the logits. It's really just a matter of preference, and we will also discuss what softmax is and what the logits are later in the upcoming weeks. So here I really want to emphasize that in the init method we define model parameters, and then in the forward method we define how and in what order the model parameters are used. So that is just like the general outline here. And this is also similar to what we have done in the previous video when we talked about the add line in the last step, in the automatic step. So here consider step 1 as the setup or module definition step, because here we are not really running any code yet, we are just setting up our Python class. So then step 2, we actually instantiate or create our model. So here I'm just setting my random seed, because if I go back one slide, here these are, like I mentioned in the code examples, these will be based on small random weights. Personally, I like to have my code reproducible, so I usually set a random seed before I initialize the model. So every time then you run the same code, it will use the same random seeds if I use the same value for random seed. However, in neural network training, of course, it requires sometimes to change the random seed, because sometimes you can have bad starting weights. I will talk also about that more later. So I'm not always using the same random seed, but if I want to reproduce these experiments, I write down the seeds I use, and then if I have someone else execute the code, they can use the same seed. And anyway, so here we initialize the perceptron model, and then this is an optional step, to device. This is really very, very cool if you want to run your code on the GPU. So the only line of code you really need to change, I mean, there will be some other lines, but the main line you have to change is this one. If you provide GPU setting here, it will run all the code on GPU. So it will transfer all that code to the GPU and run automatically on the GPU, which is really convenient. And then another thing we set up is the optimizer here. So here, like I also explained in the previous video, it gets the model parameters. In this case, if I go back one slide, sorry, we have a lot of model parameters here. All these linear ones contain weights and biases. So here we tell the optimizer what are the model parameters, what needs to be updated during gradient descent. So this is stochastic gradient descent that we discussed also last week. So it's a stochastic gradient descent optimizer. Later we will see there are other types of optimizers, like different flavors of stochastic gradient descent. Alright, so this is what I described before. So we can provide, if we have a CUDA device, a GPU, we can specify it here, and then the code or the model will be executed on the GPU, which can make training much more faster. And on Thursday I will show you some free platforms where you can use a GPU for free. Alright, so step 3 is then the training step. So that is also the same concept as I explained in the Adeline code in the previous video. So much of it, what I'm showing you here on the slides, is really very similar to what I've shown you in the previous video. I'm just walking through this a little bit more slowly. So here I have my loop over the epochs. Notice that we set model.train. This is a good practice because later there will be certain functions where we have a different behavior during training and evaluation. For example, there's a concept called batch norm or dropout, and it's a good habit in each epoch to set it to .train, and then when we do some logging or evaluation, to set it to .eval. It's just a good habit, so that is something it's always good to do. So I will also make sure in my code examples that I provide to you that this is indeed specified. And also notice you don't really have to memorize this, because in practice, when you write a new neural network or implement a new neural network, you would never start from scratch. You would never start with a blank empty script and write down all these codes. What you would do is you would copy and paste the code here. You would copy and paste this as existing code, and then you would just optimize or modify it. So you would never really start from scratch totally. So in that way you don't really need to memorize, you just have to know where to find this information. If you want to write some on code, you use usually a template to start with. Where was I? Okay, so here we iterate over the epochs, here we iterate over the batches. There will also be a training loader that I will show to you, where we batch up our training set in a PyTorch data set context that makes also the iteration over the mini batches a little bit more convenient. Here, this is like a requirement because I created this example for MNIST, and MNIST are images 28 by 28, and my model here is a fully connected network. It needs this long tabular data set, this long vector, so I'm just reshaping it, but this is a detail, don't worry about it here at this point. There's one more thing. If my model sits on the GPU, also my data has to sit on the GPU. So that is something that is required. We can't do a computation, let's say a multiplication or matrix multiplication between a matrix sitting on the GPU and the CPU. They have to be either both on the CPU or both on the GPU. So personally, how this can be very, very easily handled is by specifying somewhere in your code something like device equals to either CPU or GPU. So usually there's something you want to use like torch.device, torch.device, and then you would either set it to CPU or let's say the CUDA device. Usually if you have one GPU, you would set it to 0. If you want to use a second GPU that you have in your computer, you can change it to 1. So this is really an index here. But I will also talk more about this in the next lecture. So if you set this somewhere in your code, then this variable will be used here and here. So you don't have to change anything. So it will just work whatever you have, either CPU or GPU. So then moving on, this is the forward pass. So this is the forward pass of your model. Notice that we don't actually call forward. We don't do model.forward features. We just call model features. It's almost the same thing. I actually have a note here to remind you of that. It's actually the same thing, but there's one extra step if we don't do forward. So internally Python, how classes work in Python, there's something called a call, and this one will actually do some extra stuff and then inside run forward. So if you do it like this, there will be another method .call, basically .___ call, and this one will do some checking, just making sure everything looks okay, and then run .model or model.forward. So in this way, this is usually how we do the forward pass. Looks a little bit weird, but this is like how the forward pass works. Then we compute the loss, set the gradients to 0 from the previous epoch. That's something I explained in the code in the last video. Then we do the backward pass to compute the gradients, and then we update the model parameters. So that's the major part in the training loop. And like I said, you can always copy and paste this code and just adjust it to your new network. You never really have to memorize it. Personally, I also, I've done or looked at this so many times, I could probably write this down. But why memorizing this if I can just use existing code and just manually adjust it? What's really only important is that you understand this. You have to understand what's going on, but except that you don't have to memorize code. And like I said, no one does that. All right, there's just some more written stuff of what I explained. So you can also, on the slides, read through this more slowly. It's just some annotation. So if you want to take a look at it at home in a quiet moment, you have also my annotation here. Sometimes easier to listen. Sometimes it's easier to read than to listen, I think. So in a way, I annotated everything. All right. And this is also something I will explain when we talk about logistic regression and multi-layer perceptrons, why we use logits. All right, so the main point here, the remaining point in this video, is that there are two types of API in PyTorch. There is the object-oriented API and the functional API. And we can actually use both or a mix of both. So with functional, I mean functional programming, like the concept of functional programming versus object-oriented programming. So functional usually means that we have something without an internal state. So the torch.nn functional API is an API without an internal state. So what that means is, if you take a look at the left-hand side here, this is the perceptron that I showed you earlier in this video. So where we define the parameters in the constructor, in the init constructor, and then we call these things. Notice that for certain parts where we have this f, so I'm importing torch.nn.functional as f just for brevity. So in certain parts I have this f here. So this is all using the functional API. So I could have done it differently. I could have defined relu as a class. So here I could define it as a class. However, this would be a little bit overkill, because if you think about it, what a relu is just a function max, let's say x0. It just returns whatever value is higher, right? So it's like this piecewise function. It doesn't have any weight itself or any bias unit or weight parameter or something like that. It's just a function. So for that, it's kind of overkill to implement it as a class, because classes usually create objects, and then this object, it doesn't have any parameters, so it's kind of overkill. We can just use a regular Python function for that. So this is like the difference between using an object-oriented and a functional API. And where does it matter? So like I showed you before, on the left-hand side is again the implementation I showed you, where I created these weights here, the layers, the weight layers, and then I'm using them in the forward pass. However, there is something that is more convenient. It's the so-called sequential class here. So the sequential class executes things in order. So you can see here my forward method on the right hand side is much shorter than on the left hand side. So what's going on here? So here on the right hand side, I'm using sequential. It's essentially like a Python list, and everything that is inside essential gets executed linearly. So one by one. So first it will execute linear, relu, linear, relu, linear. But it won't, so how can I say that? It will define it first. So it will define it in the sequential thing, and then we can use it in forward. So I really like this because it's very compact, but it's using this object-oriented API here. But it's still compact because here we define the parameters, and then we have to memorize them in what order we use them, and then here we call them. See that? So here I have linear 1, linear 2, which I have here in the same order. And if you have a deep neural network with, 20 layers or something, it's easy to make an error and copy and paste some values and accidentally copy and paste them out of order and make mistakes. With a sequential one, here you define the order when you create the thing, and then let's say I'm assigning it to my network, and then here I'm calling it my network, but I don't have to redo all the forward paths. It's automatically in the sequential thing. So I like this. Actually, back in the day when I learned PyTorch the first time 4 years ago, I was using mostly this API because I felt like, okay, this is better because I'm avoiding the object-oriented API for things that don't have attributes. But then over the years, I kind of learned to prefer this API because here it's harder to make mistakes. It's easier to define everything in the right order here, I find. But sometimes, of course, we also, we need to be flexible. Sometimes it makes more sense to use the API on the left-hand side. For example, if we have custom research projects where we want to tinker a little bit more with the code, because there's one downside of the sequential API. So the sequential here, the sequential class, the problem is if you want to get intermediate results. So with that, I mean, if you want to know what, let's say, the size of this one, or there's a bug or something, and you want to print the output of this one. So if I go back one more slide, here, anywhere here, let me use a different color, anywhere here, I can just insert a print out, for example, to print the output value of this one, if I'm curious at it, if I want to look at it. It's very easy to just insert a print statement. On the right-hand side, you can't just insert a print statement here. It won't work. For that, we have to create so-called hooks. So we have to compute, for example, a forward hook or register a forward hook. So that means really we are hooking into this API. So you have to kind of first take a look at the order, so the indices. So here, after implementing this sequential thing, this should actually be not net, but my network. So if I print out my network, you can see there are these indices 0, 1, 2, 3, 4. It's essentially like a Python dictionary almost. And then I can access this. So if I want to have, or if I want to see the output after this linear unit here, I can access it here, register this forward hook. It's a little bit weird. But then when I call the model, it will print the output here. So it will print out the result that comes after here. It's instead of inserting this print statement here, I have to register this hook. And you can see this is actually more work to register this hook. So sometimes it can be a little bit more cumbersome to use the sequential API. In some ways, it might be easier to do it like this, where we can just play around with it more. However, like I said, if you have a very large network with like 28 layers, it's also more easy to make a mistake here, to somehow have some repetition here or things like that. And if you have only this one where you define it in order and it gets executed in the same order you define it, it's harder to make mistakes. So you have to decide for yourself what API you prefer. I mean, it's really up to you. There's no right or wrong. Both work the same way. It's just a matter of, I would say, matter of taste. And I will probably switch more to the sequential API for the code examples I provide to you, but you can also, for your class project, use whatever you like. But also, if the multi-layer perceptron stuff is a little bit more too complicated, we will talk more about multi-layer perceptrons in next week's lecture. So that will be also something we'll be revisiting. So you don't have to memorize any of that stuff right now. You will see that multiple times later in this class again. One last thing about PyTorch and style and things like that. So I found a very cool GitHub repository recently, a couple of months ago, where someone wrote down like the best practices for PyTorch, and I thought that might be also something cool to look at. There was also an interesting section about Jupyter Notebooks versus Python script, and that's exactly what I was also recommending. So the person here recommends also to start with a Jupyter Notebook to do some exploration and stuff like that, maybe do some coding, basic coding, and then later on move everything to Python scripts and deploy it on a server. It's like, because there are some advantages of using Jupyter Notebooks, but there are also some advantages of using Python scripts. Personally, for teaching, I really like Jupyter Notebooks because, like you've seen before, I can insert figures and show intermediate results and things like that, which is really cool. But it's a little bit more inconvenient to run Jupyter Notebooks on a server. So here also, like the person mentioned, the files can become huge if we have one single Jupyter Notebook. And because especially if you print the output in the notebook, they will become very long. And sometimes computation get interrupted in Jupyter Notebooks for some reason. So in that way, it's also not ideal for long training. And it's easier to make mistakes in Jupyter Notebook because I find the debuggers are not that good. I mean, they list here debugging as a pro argument. Personally, I find debugging in Python scripts honestly easier because you have more helper functions or utilities in, for example, PyCharm or Visual Studio Code. I most of the time use Visual Studio Code, but also many people use PyCharm, which is also very nice. So Python scripts have the advantage of that they are more robust when you want to run longer computations, and it's also easier to track changes if you use GitHub and want to look at changes, although there are some plugins for Jupyter Notebooks, but to be honest, it's still simpler with Python scripts. I find debugging easier with Python scripts. However, also like they say, it means rerunning the whole script. But an advantage of Jupyter Notebooks is that you can run one computation or one cell at a time. But either or, there are pros and cons on both sides. As a deep learning practitioner, I think you probably want to use a mix of both, maybe for simple things and analyses, using Jupyter Notebooks, and then later on, if you have more sophisticated projects, using Python scripts. In this class, I will also use a mix of both. I think for teaching, Jupyter Notebook is really nice, but for some codes that I will provide later, I think Python scripts make more sense. All right, last thing also from this GitHub repository. So here also some recommendations regarding the naming conventions. So usually we use lower case conventions with these underscores for package modules, for instances of objects, methods and functions, and variables. And for constants, we use capitals with underscores. It's just a common convention. That is also what I'm going to use for the code in this class. It's like a common convention. Okay, but you can read through this README sometime also later during this course. It's not like super important, but if you read through this rather earlier than later, then you don't learn, let's say, bad habits that you have to unlearn later, so it doesn't hurt to read this. And more PyTorch features will also be introduced step by step later in this course when we start working with more complex networks. Because, I don't want to bombard you with too many things right now because you haven't really seen the more complex networks like convolutional networks. So there will be many things we will introduce one by one when we need them. So this was more like the big picture. I hope that made sense to you. And if not, we will see this multiple times again in class. So we will be using this general PyTorch layout for almost everything. All right, so with that, that was the week here, or the first part of the week, talking about PyTorch. It was a little bit long. I think the Thursday lecture will be a little bit shorter. I just want to show you how to use some free computer and GPU resources. And that is, because it will probably be shorter, also a good time then to catch up with other things in class. All right, so see you on Thursday then.